Let's go into the obstacle manager class and actually implement the spawning logic for this new obstacle. Here, go into the spawn random obstacle method. And now we basically need to say, randomly determine if what we're going to spawn is a cactus group or a flying dino. Let's say the cactus groups have a spawn rate of 75%, and the pterodactyls, the flying dinos, have a spawn rate of 25%. So let's say int cactus group spawn rate and int flying dino spawn rate, like this. And I will create constants for those values in a second. Actually, here we need to check if the current score of the scoreboard is greater than or equal to the flying dino spawn score min, then the chance is 25%. Otherwise, it will be 0. Oh, oops, there. Otherwise, it will be 0. And now we can do something like random next to generate a random integer, and the min value will be 0, and the max value will be cactus group spawn rate plus flying dino spawn rate. Where is it? Oh, I misspelled it here. Like this, plus flying dino spawn rate plus 1, because the maximum value here is not inclusive. Let's just call it RNG. And then let's say if RNG is less than or equal to cactus group spawn rate, then we simply want to spawn a cactus. Move this logic here into this if block. And otherwise, we want to spawn a flying dino. So let's say we haven't reached the minimum score yet. That would make the flying dino spawn rate 0. So we will then generate a value between 0 and 75. So that means that this condition will always be true. And we will always spawn a cactus group. So, but if we've actually reached this minimum score, then it will actually generate a value between 0 and 100. And yeah, then it might actually happen that this condition is not met, and then we will spawn a flying dino. So let's go ahead here and say obstacle equals new flying dino, pass the T-Rex, pass the position. Now let's see. Oh yeah, we need to randomize the vertical position here. How are we going to go about that? Let me just pass 0 here for now. And I will take care of that in a second. I would just want to take care of this first. Yeah, how are we going to go about the vertical positioning? let's say, oops, new vector 2. Here we can pass the window width again, and here pass pos y. Oops, sorry about that. Pos y. There. And now we just need to come up with a way to generate this y position value. Let's take another brief look at the original game. I'm not sure if it's actually just 2 or 3 predetermined values that it randomly chooses, or if it completely randomly generates the y position. I'm pretty sure it's predetermined. It's a set of predetermined values. It's either low, which is completely directly above the ground. Then there's the possibility for it to spawn slightly above the ground, so I can duck under it. And then there's the possibility that it spawns all the way up in the air. So there's really just 3 possibilities here that are predetermined. Pretty much. Yeah. One directly above the ground, one one directly above the ground, one that is slightly up in the air so I can duck under it, and one that is actually all the way up in the sky. So yeah, let's do it like that as well. So we need to randomly select one of those predefined y positions. Yeah, there's a simple way for us to achieve that. Let's go up here and let's create a private static read-only integer array. Let's call it flying dino y pos no, flying dino y positions. That's okay. And this will be a new integer array where we store the 3 possible y position values. Maybe 90. Then 90 would be the one that is directly above the ground. Then the second one that is slightly elevated is, let's say, 60 maybe, or 50. And then there's one that is all the way up in the air. Let's say that's 20. Not quite sure. We have to play with those values again. And now we need to randomly select one of these values here. That's pretty easily done. You can just say int, let's say vertical pos index, and we're going to use the random instance here to generate a new integer between 0 and the length of this array. And then we can use that random integer to get a random element from this array, like this. And since integers can be implicitly converted to floats, we can just directly assign this without casting or anything. And now here we can just pass this pos y variable, and then that'll be that. And I think that's already it. Yeah, let's test this. And I'm guessing that these values that we determined are not quite correct. We need to change them a little bit, adjust them, but let's see. So the pterodactyls shouldn't be spawning until we've reached 150 points. And it did spawn, but it spawned at the wrong place. And yeah, obviously, for some reason here, I passed the width of the T-Rex sprite, which is completely insane. Actually, it has to be the window width, of course. But I felt like the Y position of the pterodactyl was actually not that bad. Let's see. So they should be spawning starting from now. There's one, and it's directly above the ground. Perfect. I guess the one that is slightly elevated needs to be a little bit lower, because I'm able to actually fly to run underneath it without ducking. So that's it's not ideal. So let's actually move it down a little bit. So let's say maybe not 50, maybe let's say maybe 60 was actually okay. Let's try that again. And they should be spawning now. There is one. Oh. But yeah, I guess the height is actually okay. I guess we can even lower it a little bit more. Let's say maybe 62. And here, let's say maybe 24. So let's actually go with 12 here or something, or maybe even 10. It's obvious. The thing is that the collision box of our T-Rex does not shrink down when we duck. So it will be the same either way, whether we're ducking or not. So yeah, sorry for that. That was me messing up. That was stupid. Let's go back into the T-Rex class here and actually go here in the collision box and then say here if state equals ducking, then we need to decrease the size a little bit. So we have to move it down a little bit. Let's say by maybe 4 pixels or 5. So let's say box y plus equals 5 and box height minus equals 5. Let's try that. There we go, and now let's duck. Oh, come on. Obviously still too large. So maybe 5 is not enough. Let's say 8. How large is our sprite actually? It has a height of 52. So let's take a look here. So when we duck, yeah, we should actually decrease the size quite a lot. Here, Oh, yeah, let's actually decrease it by 20 pixels. Like that. Let's try again. And now we should actually be able to duck under the pterodactyl. Sorry, I didn't realize that before. Okay. Okay. Yep. Great. Perfect. That seems to be fine. Let's try that again. Let's actually try to jump over the one that is slightly above the ground, this one. And that works fine as well. Let's try to jump right into it. To see if the collision box is okay now. Okay, yeah, I jumped right into it. I guess that's fine. And one more thing. First of all, let's define a constant for this here. Let's say private constant int duck collision reduction. I don't know. And use this constant value here. Okay, one more thing is that actually, since the pterodactyls are actually flying towards us, they should move a little bit faster than the cactus groups. So that means that here, let's see, in the update method of the base class of the obstacle, we actually move the X position based on the current speed of the T-Rex, and that is fine. But we also need to factor in the speed of the pterodactyl. Let's see. I guess we can just go ahead and say position equals new vector. And then here we can set it. Oh, actually we can't set it because the setter is not accessible. Let's go into the base class here, the obstacle class. Yeah, the setter of the position property is private. Let's change that to protected so that we can change it in the subclasses here. Now there's no more compiler error. And here what we want to do is say the X position should be the current X position minus the T-Rex's speed multiplied by the total seconds that have elapsed divided by 8. So that way we can say that so basically what this will do is it will make the pterodactyl move an eighth of the current speed faster than the T-Rex, if that makes sense. Let's see. Yeah, I guess this makes sense. So we use the current speed, multiply it by the number of seconds that have passed between the frames. Then we just divide it by 8. So yeah, let's test that. So the pterodactyls should now move slightly faster than the cacti. And it seems to be working. I just want to have the cactus and the pterodactyl on the screen at the same time, so it's easier to tell. Come on. I should probably increase the spawn rate a little bit. But it definitely feels like it's actually flying towards me. Yep. It's definitely working. I'm just not sure about the actual value, if we should actually use 1/8 of the current speed. Oops. Or maybe we should just say I don't know. Maybe we should just define basically a constant value for that, so that it always moves, I don't know, 20 pixels per second faster than anything else. And I guess that makes sense. So let's not make that dependent on the speed. Let's actually say, let's go up here and say, speed pixels per second. And that'll be, I don't know, let's say 30. Well, that's a bit low, isn't it? Let's say 80. 80 pixels per second. And then we can say here, position X minus speed PPS multiplied by game time, elapsed game time, total seconds, and cast that to a float. Let's test that again. I think this will be better. Yeah. Maybe 80 is a bit much. Maybe let's reduce it to 60. I'm not sure yet. Actually, it's okay. Yeah, let's stick with 80. That's fine. If you want, you can adjust that value a little bit. I'm going to stick with 80. I guess that's okay. Okay, and that's it for the flying dinosaur. Perfect. So we successfully implemented both obstacle types, and now we can move on to the next part of the game. All right, what I want to do next is I want to implement this little flashing animation that occurs after every 100 points. Let me show you what I mean here. Let me open up the original game. There we go. So if you take a look at the scoreboard at the upper right corner, every 100 points, it plays a little flashing animation. So basically it flashes 4 times and plays a slightly obnoxious sound. And yeah, we haven't implemented that so far. So maybe let's take care of that now. So let's see. Let us go into the Scoreboard class. And first of all, what I want to define is the duration of each flash in this animation. Let's go ahead and create a constant. Of type float, and let's name it flash animation frame length, something like that. And that'll be, I don't know, 0.2 maybe. Let's see, let's just try that. And also we need to define how many times it should flash. Constant integer flash animation flash count, and that'll be 4. Okay, so basically what we need to do is we need to check if whenever we adjust the score, whenever the score increases, we need to check if the hundredths digit in the score has changed, and if so, we need to play that little flashing animation. And the flashing animation will simply be, we can simply achieve that by basically switching off the rendering of the score text on and off. So yeah, let's do that. Let us go here into the update method. Here's where we adjust, where we increase the score over time. And let's actually go here and create a new local variable of type integer. Let's call it old score and assign the display score to it, which, remember, is just the score cast to an integer. Now, let's see. We need to check if the hundredths digit in that score has changed. So, how can we achieve that? I guess what we can do is say if display score divided by 100 is not equal to old score divided by 100. So this is integer division. So this will always crop off any remainders. So let's say the display score, let's say the old score is 199. Dividing that by 100 in an integer division would give us 1. And let's say the new score is 200. And dividing that by 100 in an integer division, obviously that's 2. So if that is not equal, yes, then we need to actually play that animation. And to indicate that this animation should now be played, maybe we should introduce a new field. Yeah, let's go ahead here, create a new field. Private boolean is playing flash animation. And another one of type float named flash animation time, which will store the time in seconds that the animation has been playing. So if this condition is met here, we simply set this field to true, and also no, that's it. Now we also need to, yeah, we also need to set the time to 0. And then let's put another condition here. Say if it's not already playing and this other condition is met, then do this. And then let's go down here. If is playing flash animation, then we say flash animation time plus equals game time, elapsed game time, total seconds, which is a double. We need to cast that to a float because our field is of type float. So now we increase the time that the animation has been playing. And let's see. We created a constant here, right? Frame length. Okay. Maybe let's go here and say if flash animation time is greater than or equal to flash animation frame length multiplied by flash animation flash count. That would mean that we have reached the end of the animation. So let's set is playing flash animation back to false. And now we need to also take care of the actual flashing of the text. So let's see. I guess what we could do is go in the draw method here and say we only want to draw the score if it's either not playing the animation at all, or if it is playing the animation, and basically we want to render the text every second frame of this flashing animation. So I guess a way for us to achieve this would be to let's say we take the flash animation time, we divide it by the frame length, and then we cast the result of that division to an integer. Whoops. And then do a modulo operation, modulo 2, and if that equals 0, then the draw, well, let's say if it doesn't equal 0. So this is a little bit, I guess this is a little bit hard to grasp, but this should actually do the job. So flash animation time contains the time in seconds, how long our flash animation has been playing. If we divide that by the frame length, and then cast that to an integer, we should basically get the current frame within the animation. And then if we do a modulo division here by 2, basically what we do that way is we check if the number is even or odd. And then we basically say only draw the score on each odd frame within the animation. I think this should already work. Let's give it a try. Whoops. Oh, it doesn't seem to work. Did I forget something? Well, first of all, I think we should add a set of parentheses here. But that is most likely not the problem. Let's see. It's definitely not playing. Maybe let's use a more extreme value here so we can see it better. Let's say let's actually go with, maybe 1 second is a bit much. Let's say half a second. It's not really extreme, but half a second should be visible to us. Let's see. Oh, whoops. This is the high score. Stupid me. Messed it all up. So let's test it again now. Ah. Come on. Okay, I'm super unlucky, or just super bad at the game. Or both. Yeah, there we go, it works. But I forgot something. First of all, let's say 0.4 or maybe 0.3. 0.333, so basically a third of a second. And then we need to actually here if we want to make it flash 4 times, we actually need to multiply the flash count here by 2. Or, hold on. Yeah, right. We need to multiply that by 2 because one flash is basically just the score disappearing. And if we have only 4 frames, obviously that's not enough. We need 8 frames, and four of them being the score being rendered, and 4 of them the score disappearing. So now it should actually work. Ah, come on. Yeah, perfect. It flashed 4 times. Great. And now we also need to make sure that it also plays that slightly annoying sound effect. And for that, we're going to add a new field here, private sound effect. Let's call it score SFX. Then here in the constructor, we're going to pass a sound effect and initialize the field accordingly, like this. And let's go into the TrexRunner game class. And somewhere here in the load content method, here, we need to actually pass the sound effect to the constructor. Here, it's this field here, SFX score reached. We're going to pass that to the constructor. Now, if we go back into the Scoreboard class, we can go down into the update method. And then here, as soon as the animation starts playing, we simply call the play method of the sound effect. And this should do the trick. Let's test it. Yep. I mean, I barely made it, but I did hear the sound effect. There we go. That's really annoying because it's really loud. But yeah, that's definitely working. I will actually decrease the volume here a little bit. You can actually pass, or can I just, is there maybe a property for master volume or something? No. You can pass an argument here for the volume. Let's say 0.8. Zero. And it's also 0. Oops. So just to make it, whoops. There. Just to make it slightly less annoying, I'm going to lower the volume a little bit. Yeah, still a little bit obnoxious, but not as bad as before. Yeah, I think actually looks great. Whoa. Oh, I think I just discovered a bug. Let me check something. I think the pterodactyls actually keep moving when we're dead, because they're still factoring in their own speed. So even though the speed of the T-Rex is 0, they still have their own speed going on, and that's why they keep moving a little bit. Let's just test that. Yeah, it definitely keeps moving, which is weird. So let's fix that. Let's go into the Flying Dino class here. And yeah, actually we need to, let me just go here, right click on this if statement. Let's say add braces. Now I'm just going to move this positioning logic into this if branch. So only manipulate the position if the T-Rex is actually alive, and that should fix the problem. Let's see. The sound is really annoying. I will lower the volume even more. Let me just take care of that now. Scoreboard, and here let's go with 0.5. Oh, come on. Yep, so now it no longer awkwardly keeps moving even though the game over screen is showing. So yeah, that's fine. Okay, so we got that taken care of, so let's see what we can do next.